Herkese merhabalar. Bugünkü webinarımıza hoş geldiniz. Ben Ekin Akın Korkut, BİAS'ta lisanslama ve eğitim uzmanı olarak görev almaktayım. BİAS Mühendislik, makine mühendisliği disiplinleri çerçevesinde ileri mühendislik çözümleri sunan bir firma olup, Ar-Ge, CIA yazılımları, test ölçüm sistemleri satışı, proje analiz ve test ölçüm hizmetleri ana çalışma alanlarıdır. Detaylı bilgi almak için web sitemizi ziyaret edebilir ya da tüm sorularınızı info@bias.com.tr üzerinden bizlere iletebilirsiniz. Bugün Türkiye'deki temsilciliğini gerçekleştirdiğimiz P7 firmasından Nina Mulo bizimle beraber. Fast and Optimal Design of Your Automotive Components with Adams Car and P7 isimli webinarı kendisi gerçekleştiriyor olacak. Webinar dili İngilizce olacaktır. Webinar esnasında ileteceğiniz tüm soruları chat üzerinden iletebilirsiniz. Webinar sonunda tüm sorular cevaplandırılacaktır. İlk olarak Ahmet Kozanoğlu bizim için kısa bir sunum gerçekleştirecektir. Sözü Ahmet Bey'e bırakıyorum.
Ekin Hanım teşekkürler. Thank you very much Ekin. Normally I am planning to do in Turkish, but we have some foreigner guests, so I will continue in English my presentation. I will do a quick introduction of P7 software, integrate and optimize your process. Firstly, I want to introduce myself. I'm Ahmet Kozanoğlu. I'm working in BİAS as a CAE team leader since 5 years. And I am also responsible from P7 Cradle CFD and Upstream software. So, sorry for Turkish presentation, but I will continue in English. Firstly, if we examine it from traditional design cycle, firstly, the CAD model is created and design revealed. There's our pointer. And then the design is put into analysis in a virtual environment, and strength of the structure is examined. For example, you can use ANSYS, MSC softwares, or any other solvers. The model should be built, and the analysis result should be obtained, and the result should be examined from analysis engineer, finite element or CFD analysis engineer. If the results do not meet the requirements when the result examined, the first step should be returned to the design phase and should be made again. Then an analysis model should be made for the design again, and this structural or CFD analysis will be repeated again. So these must be the traditional optimization and traditional integration. Firstly, you start with NX or CATIA or any CAD tool. After you design it, you build a model and run in finite elements solver or CFD solver. After that, you examine your results and you think about it's optimum or not, it is meet our requirement or not. After that, you can continue with this cycle. So there's too much manual analysis in this phase on traditional optimization. So sometimes you can get some error from in data, some data. So because of this, we can continue in modern optimization tool. Also, if you have a one requirement for the for one design criteria for your structure, you can do it this way, traditional. But if you have more design criteria in for your structure, so you have to use some modern optimization tool. In the case that we mentioned in the previous slide, only one design criteria, but in this one we have two different design criteria. So most problems and most structures, more than one output is examined for the optimum target of the structure. For example, for this problem, another output could be that doesn't distort its behavior at high temperature. It's high temperature. So we are using for modern optimization and integration, we are using P7 software. P7 software has three products. One of them is P7 Core, the other one is P7 Desktop, and the last one is P7 Enterprise. P7 Core can be defined as a Python integrated library, program without an interface, and users can access and use all the algorithms and techniques in it. For P7 Desktop, we have 4 legs. We can define a legs. Firstly, you integrate your workflow. You can use CAD tool, you can use CAE tool, and integrate all of them to P7 Desktop. After integration, you can automate your process. And after automation your process, you can obtain optimum results. For example, you want to decrease mass of your structure, so you can get an optimum result. And you run, for example, 100 analysis in P7 Desktop. You can get 100 input and 100 output. So you can use this data for your prediction modeling. Last one is P7 Enterprise, but in this webinar, we will continue with P7 Desktop version. So on P7 side, you can integrate the process you repeat constantly on the P7 platform. As I said, we can integration, automation, Design Space Explorer, and predictive modeling. So after modeling once, you can get countless analyses with single click with P7. You can manage the process and that you automate with optimization tools, and you can get the most suitable configuration for your system in a shorter time with this algorithm, algorithm that in P7. So after that, you can use P7 predictive modeling tools, and you can examine the data that you obtain before or obtain in a test results, and create a high accuracy mathematical models from this data and predict the results without waiting simulation time. So P7 has the ability to manipulate and run your both CAE tools, both CAD tools, and other software tools. In this way, you can model the process you run manually as a workflow, integrate the programs or tools you use in the process, and run them automatically. And as you can see in these slides, it's possible to provide integration different ways, direct integration and general integration blocks. You can use it. Of course, we have some softwares in Star CCM, ANSYS, MATLAB, NX, etc. But if your CAE tools or CAD tools run with batch commands, you can integrate to P7. So there's no problem for that. The same operations can be performed for any other engineering software using general integration blocks. And with this feature, almost all engineering software can be integrated. For example, we don't see LS-DYNA or Gradle CFD or any other software, but you can integrate with program block, because every software, most of the softwares run with batch commands. So you can introduce your program to P7, and you can run with run your program in P7. And after that, in addition, Fortran or C++ programs can be integrated on P7. And also scripts or in-house tools that you developed within your organization can also be added for workflow. So in this way, you can completely automate your process. As an integration of process, every CAE engineer knows that we have some input file. We have also some output file. You introduce your input file to P7 and select some boundary condition or design criteria or any other things. So after that, you run in your program block, and after that, you can get output and look at your von Mises stress, or your mass, or your lift coefficient or drag coefficient, etc. Sum up to integration issue, P7 enables you to work by coordinating CAD and CAE software and data source transfer, in-house tool scripts or programs. In this slide, actually, Nina will tell about this slide because it used Adams car, and Nina's presentation regarding on Adams car. We done to integration and automation process, and after that, you will do it with optimization. When we look at optimization, all you need to do in your optimization studies, determine the parameter limits and run the button. P7 automatically takes as many analyses as necessary and can direct study in the most effective way according to mathematical algorithms it uses in background. I mean these techniques, optimization techniques, and you can also use smart selection on this one. For example, you have 3 different design criteria with lower bound and upper bound, and you have 2 response with F1 or F2. And when you change the type of response, smart selection, thanks to smart selection technique, will automatically update it. When you minimize or constraint, it use adaptive design for minimization, surrogate-based optimization, etc. So with smart selection, you don't have to know the background of these optimization techniques. So you just define your input and output and what you want to input, I mean response, minimize, maximize, adaptive, constraint. You can enter this type and after that run your analysis. So P7 also provides to our engineers with the best optimization result by saving time, because if it's in manual, I mean traditional optimization phase, it takes too much time. But for this one, just the computer run the solutions and select different design criteria and show the different response. So you don't have to sit in front of your computer. You just run it on local machine or on a server machine, and you can continue the other works. So it also allows them to easily select the best optimization technique and accurately investigate the results. The third one is optimization, and the last one is predictive modeling. So by feeding the obtained results or test data as an input, you can create a predictive model and predict your results within a second. Even if you have test data or you have lots of analysis data, if you have both input and output your system, you can create a predictive modeling on P7 and predict within a seconds for your results. So what is predictive modeling? What can I say? What's predictive modeling specifications maybe? Generate fast and robust prediction models with automatic technique selection. It also uses smart selection for creating in predictive modeling. It also uses smart selection. Validate reference data to find the best approximation quality and explore the behavior of multidimensional models by examining input and output dependencies and export. And finally, you can export your model the external files. So thank you for listening and participation. Now I will now give the floor to Nina Moel for her presentation titled Fast and Optimal Design of Your Automotive Components with Adam Carr and P7. Nina?
Yes.
Did you hear me? Yes. You can share your screen and you can start it. Thank you very much.
All right. Thank you, Amit. Welcome, everyone. So you should be able to see my screen now.
Yes, I can see it.
All right. Thank you. So thank you, Amit, for this nice presentation of the general capabilities of P7. So now my focus will be more on the specific use case, as you may know, with the Adam's car. So just to present myself briefly, my name is Nina Muelo. I'm working at P7 as an application engineer. So working from Toulouse, the headquarters of the company. I will present also the company briefly. And today my talk is about a fast and optimal design of an automotive components with Adam's car and P7. All right, so just briefly to introduce P7, because maybe some of you don't know who we are. So P7 is a software editor which provides tools for machine learning, optimization, collaborative engineering, and low-code automation. So some diverse topics on which we will elaborate after that. The company was founded in 2010 and is actually a spin-off of Airbus. So all the algorithms that we will refer to were initially created by an Airbus research organization. But now we are totally independent since 2015 and still based in Toulouse with regard to this origin, let's say. But we have employees worldwide and we provide our software worldwide as well. You will see the diversity of customer that we work with. And we also have some partners all around the world, including Bias in Turkey, for example, which helps us to resell the software in different countries. Regarding our customers, so as you may see, we are providing the software to different domains, different industries. Of course, the aerospace and defense with respect to our origins with Airbus, but also the automotive industry, the energy, and many others, just based on the fact that we are providing mathematical tools, right? Or let's say automation tools, but not something specific to a certain domain. So we can cover very diverse subjects. This is one of our strengths. And this is why we have this diversity of customers. But to tackle this such diversity, we provide different tools. So here is the P7 product line. So as Amit said, everything started from a Python library, which is named P7 Core. So this one embeds the root algorithms that we use for our three main topics. So design exploration and design of experiments, optimization, and predictive modeling. Okay, so this is all included in the P7 Core, and that was created with, let's say, or from the Airbus Research Center. Now that we are independent, we also wanted to, let's say, tackle different population. And in order to apply those algorithms to engineer profiles, the goal was to provide a desktop application with a graphical interface, right? Which is more, let's say, user-friendly, and which also provides workflow automation with external software integration. So CAD, CAE integration, but still offers the capabilities of the strong algorithms of P7 Core. Okay, so this one is P7 Desktop. So it's an application that you can basically install on your computer and work with it. So let's say generic or some application that we are used to in the engineering context. But recently, we also faced another, let's say, limitation with this product, which is the topic of collaborative engineering. Because P7 is strong enough for like one person to work on to provide some very powerful results. But when comes the need to share the work or to work with other people or to democratize some high-level tasks, then this software is limited. So this is where P7 Enterprise comes into play, which is a cloud-native platform. So it's the same look and feel. You can also integrate your CAE, CAD tools. But on top of that, you have low-code workflow automation, collaborative engineering, so you can work on the same project with different colleagues, share your work, and service orchestration. So you can definitely work at scale with your entire company resources, and P7 will manage all of that. We observed productivity gain up to 300% on this platform, so it's quite promising. And it's also an enabler for digital twin strategies. So today, my topic is not about P7 Enterprise, but it was for you to have an overview of what we provide. So we will focus on this P7 desktop application, which is enough for the moment, just to show this CAE, CAD integration and the powerful of our algorithms for the sake of optimization for today. So again, I won't repeat what Ahmed said, but with P7, so P7 desktop, I will name it P7. You have three main pillars. So the integration and automation of external tools that could be simulation models, analytical models, or even just raw data sets. And with this integration, you can then play with our algorithms for design exploration, including design of experiments and optimization and predictive modeling with machine learning capabilities. And regarding our subject, so we will talk today about the McPherson suspension and steering system. I hope the video, yes, can start. Okay, so this is a small animation to just show you about this system. So it consists of an assembly of suspension and steering. The suspension is based around basic triangular design in two parts. So this is basically here. Okay, so we have a control arm and a radius rod. So these together form a triangle against the car chassis that we do not have on the picture. But this is widely used in the automotive industry, but still requires some refinements to be well designed and to provide some good performances to the car. All right. So here you have another schema of the same tool, same system. And the objective for today is to provide, of course, a stable and safe car. And to achieve this goal, we have two different sub-goals, let's say. The first one is to minimize the camber angle beta, which is here. Okay, by minimizing this camber angle, it will allow to have a tire which sticks to the ground. Okay, so you have the maximum surface of the tire, which is in contact with the ground. So then you have a more stable car. But we also want to minimize the roll center height difference between minimum and maximum values. So this is basically this distance here. And this one will enable to have safer cars, or again, more stable and safer. In order to play on those two aspects, we have 3 lower control arm points. Okay, so I told you that we are talking about a small triangle on this geometry. So this is exactly what you have, in red here and here on both parts. Okay, and the control arm points are those PF, PO, and PR that you have. So the front arc point, the outer arc points, and the rear arc point here. Okay, and for each of those hard points, of course, we have the coordinates, so X, Y, and Z. In total, it means that we have 9 variables and basically 2 outputs, so 2 objectives. So with this, we basically designed everything in Adams. Okay, so the simulation was made with Adams Car, which provides reliable simulation tools to model this kind of system, so regarding automotive industry. But on Adams Car, the optimization capabilities are limited. Okay, it provides quite okay design space exploration and so on, but with P7, we think we can provide more than that with machine learning capabilities. We will see that right after. And on top of that, the problem here is multi-objective optimization. We saw that we have 2 different objectives with the aim to find the best compromise between those 2 objectives, which are conflicting criteria. By conflicting, I mean that if one of the criteria is minimized, it's likely that the other one will increase, and vice versa. So we have to find the best combination of the 2 criteria to minimize them both at the same time. On the other parts, it has many variables. We saw that. We have 9 variables here, and it's too much for an engineer to search manually for the optimal solution. So this is why we rely on algorithms here and automation. And to close the loop, the industrial context now needs fast and reliable study results. So you basically you cannot afford a large amount of time to search manually for the answers and to implement that slowly, let's say. So in this general context, the question here is how can P7 bring value in solving such a complex task? And the answer will be basically by coupling those 2 software, so Adams Car and P7. To do that, we have one strength of P7, which is process automation. So P7 is, so here you see a window, an example window of the P7 tool. And inside this window, you have a kind of block diagram here, which is enlarged in this picture. And this is what we call a workflow. Okay, so workflow is basically blockchain, and each block here is responsible for a specific task. Okay, so for example, you have the design space exploration block, which is responsible for, of course, design space exploration, but I mean design of experiments or optimization. Then you can have a SolidWorks tool, so of course responsible for SolidWorks simulation, and you can have in-house tool execution, for example, here with the program block, or sub-level workflows with the composite block. Okay, so this one actually embeds another workflow inside to a different level. So this workflow will actually capture your engineering process, standardize it, okay, and with this you can capitalize on your preferred method. This is also a nice way to have a visual definition of complex computations and complex tasks with an implementation of logic operations, for example. So you have directly the illustration, let's say, of your process. You can also run with this parallel and remote executions with batch management. So this is exactly what you have on those small icons. This workflow can be distributed on different machines. Okay, so with a P7 agent, so a specific connector, you can access to other Windows remote process. With SSH connect to Linux, but we also can let's say, connect or reach HPC servers with Slurm, LSF, or Torque. Okay, so in the end, your workflow can be really managing, let's say, different machines, and also reuse different data with caching. So with this definition of process automation in P7, our goal is now to do the same with Adamscar. Okay, so on the first step, the simulation was performed on its own with Adamscar application with the following settings for those who are interested. So basically, the engineer did first simulation on Adamscar to set everything up. At each simulation step, we are, of course, computing the delta H, so this value here that we want to minimize in the future, and the beta value as well. So this camber angle here that is also to be minimized. Okay, so you have those parameter calculation for one full model execution. Okay, and in the end, those values are just computed for every time step, right? So we ensure that the model provides the good output. And then we basically build such workflow. So you see here the workflow has different, let's say, shape. So your workflow can represent basically any engineering process, and you can be quite, let's say, creative to customize your own workflow. Here in this workflow, we have 4 blocks, so 4 main steps, okay, to integrate this Adamscar. So let's start with the 2 first one. Like Ahmed said, basically for simulation tools, you can access different input files. And in our case, the input file will be the CMD file. Okay, so in our case, we have one Adamscar simulation and one small file which defines the different steps of the simulation properties. All right. In this simulation properties file, our goal is to redefine the hardpoint values, right? So redefine our front, outer, and read point values, like you have here in blue, okay, through some small comments. Okay, then, so this is done by the first text block with powerful text parsing capabilities. With no code process. So just by selecting your value with the mouse, it will be changed automatically. Then the second block is the Adamscar program. So this one will opens the assembly, so the .az file, and update the hardpoints based on the comment that we just defined. Okay, so this is what is said here. All actions are performed in accordance with predefined comment file. So to summarize, here on the first part, you change the values of those hardpoints in the comment file, and then you use this updated comment file to launch the Adamscar program. Okay, so P7 manages the Adamscar execution. Once it's done, we then switch to the next blocks. So the Adamscar post-processing is made to, let's say, export some tables with the task-related values, so this delta H and beta values, to predefined, by execution, sorry, of the predefined CMD file. So again, here we just continue the process with some post-processing tasks. And in the end, so we retrieve those kind of plots here, right? And with a small Python script, we are just parsing the results. So just by computing the final value out of those tables here, out of those graphs, to go back to P7 with the exact value of delta H and beta. All right, so to summarize briefly the whole workflow, we modify the command lines to modify the input of the hard points. Then we launch the process of Adams-Carr. We post-process a bit to output those graphs. And by using those graphs, we then just gather the final value of delta H and beta. Okay, so with this workflow, you basically have a standardized process which will take as global inputs your new output values and which will, let's say, print as outputs the camber roll center and min-max difference. Then this entire tool or entire object, let's say, is just the automation of a complex engineering process. And it's also made to avoid manual and repetitive operations. Because again, like Ahmed said, when you are dealing with manual operation, you are then facing some, let's say, human errors with, just forgetting about one file or one value or misreading something. This is totally normal. But with P7 here, we ensure that the process is the same for every task. And on top of that, the workflow provides, of course, a visual representation of the process. So it means that if you want to share this project with someone else, this second person can directly see what has been done and understand more clearly without going into the details of the simulation. So now that we have an automated workflow, our goal, of course, was to optimize this design. So how can P7 optimize such task? Well, we have different algorithms and we have different, let's say, techniques to tackle those problems. Some of them including machine learning or more traditional methods. Okay, so P7 is made to explore models in a fast and effective way with advanced tools for design of experiments, for example. So this can help into giving a better knowledge of your system. It also provides an easy and effective solution for a lot of industry optimization problems. We saw that P7 is applied in different domains. So this is where this comes from. So it's based on AI. And also it has unbeatable capabilities and flexibility for building predictive models. So this is not our goal for today's topic, but if you have some question, I would be happy to answer about machine learning. And on top of all those capabilities, we have the smart selection. So like Ahmed showed you, which helps to choose the best technique if you're non-expert in mathematical techniques. So based on that, we basically just reused the workflow we created before. So this one here. Okay, we put it inside a composite block. So again, this composite is just embedding the initial workflow. And to control this workflow now, we do not provide inputs from the user, but from P7 directly, so from the Design Space Exploration tool. Okay, this tool will also gather the results to have this kind of loop. And here the first task is actually just to explore some design possibilities. Okay, just to know more about our system, to understand what's going on, what values are affecting my outputs, and so on. To do that, you have here a picture of the interface of this block. So Design Space Exploration, it's DSE. And you see that we defined our variables, so all our hard points, the 9 parameters, with some lower and upper bounds. And in the end, we gather the responses for our 2 values, the camber and the roll center difference. We are now in the evaluation mode, which means that we do not have any specific targets for those responses. So the smart selection algorithms provides the technique of Latin hypercube sampling. This is what we call LHS, to just explore correlations between input and output parameters. For the moment, we asked for 300 points. Okay, we could afford that because we had some, let's say, free time with Adamskar to play a bit with it. But of course, if you want to decrease this simulation budget, it's totally okay, and P7 can handle very limited situations. So just by automating this task of design of experiments, we get some first results, which you can see here. So still with the P7 tools, we have access to correlation study and feature importance as well. So the part of the correlation study is represented here with the correlation matrix. So you can see each of the 9 inputs are here on the, let's say, x-axis, and you have on the y-axis your 2 outputs. So you can see based on the colors and then with the correlation coefficients, which values are affecting which outputs. So for example, we have here the hard point outer y coordinates, which is affecting a lot this RCDIF, so the delta H basically value. So in the, let's say, positive manner. So every time this inputs increase, the output also increases. But you have almost the same here. So the outer Z value affects a lot the camber angle, but in the negative way, which means that if the outer Z value increases, then the camber angle decreases. So with this, let's say, visual representation, you can also directly get to some conclusions on which value are important or not. Okay, for example, this rear X input doesn't have much impact on any of the 2 outputs. So maybe this value is not important for our simulation. You can also retrieve those results with the feature importance charts, which demonstrates the ratio of each input in influence on the regression model response. So based on linear or quadratic regression models. And you have here the, for those who know, the Sobol indexes computed. So basically you have the same kind of results, but with respect to regression models. So in the end, this, let's say, first step of the study shows the power of our algorithms to perform advanced sensitivity analysis without coding anything, nor having advanced mathematical skills, right? This is done just by P7, just with mouse clicks to create the workflow, to integrate atoms, and to get to this sensitivity analysis. Then once we had a better overview of our designs and our system, we directly switched to the optimization. So this is done with exactly the same workflow. Okay, so you see the 2 blocks are the same. We just changed the naming here from DOE to SBO. So SBO stands for the optimization process. And in this case, we told P7 that we want to minimize the responses. So both responses are to be minimized. Then the technique is adapted to an optimization method. And on top of that, we told P7 that we have 2 hints here. So we have noisy responses first, which means that our system is a nonlinear system. And we have cheap responses. Cheap means that the simulation here doesn't last for hours or even days, but maybe for some minutes. And we can afford some extra time or some extra designs, let's say. Okay, we are not very limited by the time. So P7 can allow more general search on the design space. So this is why the gradient-based optimization has been chosen here. And at runtime, the smart selection technique, so this small storm icon, will adjust actually this technique and the parameters to method convergence. Okay, so in order to get to the results more efficiently. Then we have this kind of results here. So the budget was automatically determined for the optimization because we told P7 that we have cheap responses. We also reused the 300 points from the design of experiments, okay, to gather and to capitalize on what we have done so far. So in the end, we had a total of 2,571 model evaluations for the gradient-based optimization. And from those points, we found 127 points, which are Pareto optimal. So what does it mean? It means that we have 127 points, which show a good balance between minimization of the beta angle and the delta H distance. On this plot, this is represented by the red points here. So this is basically the limitation of the green clouds points, which are, let's say, closer to this graph origin here. Okay, so because we have two objectives, the generic results of such optimization is to have this Pareto frontier. And then it's up to the engineer or to the project manager to select which design is actually the best, depending on if you want to minimize or, let's say, focus more on the camber angle or on the roll center difference. Okay, so then it's up to you to have this final selection. But this is what P7 provides. In case of expensive simulation, because I know that for some of you, maybe for CFD analysis or mechanical analysis, you may have expensive simulations, I mean, lasting for more than 2 hours, let's say. Then the surrogate-based optimization would be a nice technique and would have been chosen by the smart selection. And this one enables considerable budget reduction. So maybe this number of evaluation here, more than 2,000, is like surprisingly high. But with surrogate-based optimization, we actually use predictive models, so machine learning, to reduce the number of iteration and to go to the optimization results much faster. So in the end, with P7, you have an easy setup of an optimization campaign with the possibility to capitalize on all the runs and achieve strong goals in a limited amount of time. Okay, so depending on your task, you can definitely control how many iteration you allow P7 to perform. So as a small conclusion, P7 here as, let's say, a Swiss Army knife profile for solving engineering problems based on 3 main pillars, so technical pillars, the industry-proven algorithms and techniques. So you saw here just a small part of it, but we have actually many algorithms for solving many different tasks for different domains. In case you are not comfortable with those, let's say, math techniques, the smart selection can help, definitely, by just selecting the right technique and setting up all the parameters, even at runtime, adjusting the algorithms. And the powerful workflow automation engine to capture your workflow, so capture your engineering process. So standardize all of your methods, capitalize on it in order to reuse your project, to reuse your simulation, simulation process and so on. and also to democratize the simulation. Because if you want to share your P7 project with someone who is not aware about how Adams works, for example, well, just with a P7 workflow, someone can definitely work with Adams car, launch several simulations just by launching the P7 workflow, changing some inputs, getting some outputs, and performing very advanced engineering tasks. Okay, here ends my presentation. If you have any question, of course, I'm very happy to answer. Thank you for your attention.
Thank you for presentation, Nina.
I see no question.
I see. Is it applicable for CFD simulation? Of course, yes. If I go back to the workflow, the initial one. Oops, again a bit. Okay, so this kind of workflow is actually adapted for Adams car. But at P7, we provide very different connectors, let's say. So those blocks here relying on Adams car simulation could be actually replaced by another program. So if you're using, I don't know, ANSYS Fluent, for example, we can definitely work with ANSYS Fluent with the same process. We are totally agnostic to any software. So we work with ANSYS, Hexagon, Siemens, whatever the software, even in-house software. So I mean, even in-house codes. Can it be exe files or Python scripts or MATLAB, whatever? We can integrate any one of them. Then just with having a workflow like that, which can automate your process, you can plug on top our algorithms for optimization, design space exploration, and so on. So yes, no problem with CFD. So can P7 as a plugin for CAE and Adams? Sorry, I will exit to have a better view of your questions. So plugin in CAE or Adams integrate. So if I understand the question, it means that can P7 be launched from Adams, right? Yes, so not at the moment. We don't have any like strong partnership, let's say, with Adams. So maybe they have a connector, but in our case, our let's say process is to integrate Adams within P7 and then to work from P7.
I think there is no question in chat panel. You can contact us for any question that you have later, and
two directions.
Comment. Okay.
Yeah, so for the moment there's only one direction, at least that we know. It's Adams integrated inside P7. Okay, sorry, Amit.
Okay. So thank you for joining our webinar. Thank you, Nina, for your presentation.
Thank you. Thank you all.
Herkese teşekkürler. Görüşmek üzere. İyi günler.